Imagine a single living cell in a small dish. It can grow and multiply, but eventually it reaches the edge. It runs out of space and resources. This is a hard limit. Every growing thing, from the smallest cell to the largest empire, eventually hits a wall. For a civilization exploring its world, that wall is the total energy of its home planet. Once a species learns to use all the wind, all the sunlight, and all the heat from its planet's core, what comes next? This isn't a question of politics or economics. It's a law of physics. Growth requires energy. To keep growing, a civilization must find a much, much bigger source of power. It has to look beyond the edge of its own small dish and find a way to capture something far greater. To understand this challenge, scientists use a kind of cosmic report card. It's called the Kardashev Scale. It doesn't measure how smart a civilization is, but how much energy it can use. A Type 1 civilization has mastered its entire planet. It can control the weather, prevent earthquakes, and draw power from the heart of its world. Humanity isn't even there yet. A Type 2 civilization has graduated to the next level. It can harness the total energy output of its home star. And a Type 3 civilization is truly vast. It commands the power of an entire galaxy with billions of stars at its command. This scale gives us a roadmap for the future. It shows us the next great step humanity must take to survive and grow. The leap from Type 1 to Type 2 is the hardest. The numbers are staggering. Our sun puts out about 400 septillion watts of energy every single second. Earth receives only a tiny fraction of that, about 1/1,000,000th of the total power. To become a Type 2 civilization, we need to capture a huge part of the sun's entire output. How do you build a bucket big enough to catch the light of a star? The answer is not a giant, solid shell. Science fiction often shows a solid sphere built around a star, but that idea is a trap. A rigid structure that big would be gravitationally unstable. Any small push from a meteor could send it crashing into its sun. The real solution is smarter and more flexible. It is called a Dyson Swarm. A Dyson Swarm isn't one object. It's a massive orbiting cloud made of trillions of independent parts. Think of it as a huge collection of solar-collecting satellites. Each one flies in its own orbit like a tiny planet. Together, they form a thick, buzzing shell around the star, drinking in its light and turning it into usable power. This avoids the problems of a solid sphere while achieving the same goal. But where do you get the material to build trillions of satellites? Launching that much mass from Earth would strip our planet bare. The starting point for this project is something amazing. You have to dismantle a planet. The best candidate in our solar system is Mercury. It's very rich in metals and has no life to protect. Its location is also perfect. Being so close to the sun provides the intense solar energy needed to power the construction. We wouldn't be destroying a home. We would be turning a lifeless rock into the building blocks of our future. This is a new way of seeing the planets, not just as places to visit, but as raw materials for cosmic engineering. This huge project would not be built by human hands. It would be built by an army of self-replicating robots. The process starts with a single seed factory, sent to Mercury. This factory, a kind of von Neumann probe, has one main goal: use the planet's resources and solar energy to build a perfect copy of itself. Then, those two factories build two more. The swarm is not a random cloud of machines. It is a masterpiece of orbital engineering. Imagine thousands of dense, overlapping rings around the Sun. Each ring is a perfect circle of collectors, all moving together in a beautiful cosmic dance. This structure is alive with purpose. Each collector in these rings is a special kind of robot called a statite. Think of them like super-smart solar sails. They use the constant push of sunlight itself to stay in their exact position. They don't need rocket fuel. They float on light, making tiny changes to keep the whole swarm perfectly balanced. So, how does all that captured sunlight get to us? The process is super smart. Each statite's surface absorbs solar energy, turning it directly into electricity. This happens trillions of times a second across the entire swarm. A constant river of power is born in empty space. That power doesn't stay there. The electricity is converted into a super-focused beam of energy, like a laser or a microwave. This beam shoots through space with almost no loss of power. It travels to special receiving stations on Earth, delivering clean energy from the Sun, day and night. But building this swarm isn't just about getting more power. It's about something much bigger. It is the key to our long-term survival. A civilization that lives on only one planet is like a person living on a tiny, fragile island. One big wave and everything is gone. The Dyson Swarm is the only real way to solve this problem. It's not just an option, it's the necessary next step. Any species that stays on its home world will eventually face a disaster it can't stop. An asteroid, a supervolcano, or a dying star. To survive, we have to look up. This leads to a big question about space. If the universe is so big, where are all the other smart civilizations? This is called the Fermi paradox. One possible answer is the Great Filter. This is the idea that there are huge challenges that almost no species can pass. Building a Dyson swarm might be one of those great filters. It is a huge test of cooperation, science, and looking to the future. Civilizations that keep fighting over their planet's limited resources might fail this test. They burn out before they can reach for their star. But if we pass this test, what can we do? With the power of an entire star, humanity becomes something new. We could build giant laser sails. These would use powerful light beams to push spaceships to other stars, getting them close to the speed of light. That's not all. We could control the climate on Earth perfectly. We could stop any ice age or heat wave. We could even begin terraforming. That means changing other planets, like Mars or Venus, to have air and water, making new homes for humanity among the stars. This level of power changes the very definition of a world. A Type 2 civilization doesn't just live on a planet. It engineers its entire solar system to be a home. They can build new worlds from scratch. This changes our idea of home forever. With a Dyson swarm, Earth is no longer the single cradle of humanity. It becomes a historical monument, a beautiful starting point. The real action moves outwards. Billions of people could live in custom-built orbital habitats. These are giant spinning cylinders or spheres, each a unique world. They would float within the swarm itself. Each one could have its own gravity, its own weather, and its own culture. This cosmic idea feels huge. So how long would it take to build? With exponential construction, it's faster than you think. Once the process starts with self-replicating robots, it could be finished in a few centuries, maybe a millennium. And here's the amazing part. We are already taking the first tiny steps. Every satellite we launch, every experiment with 3D printing in zero gravity, every plan to mine an asteroid. These are the seeds. They are the first letters in a very long story. But building this future brings huge, unanswered questions. What does this do to our sun's appearance from other star systems? A star that slowly dims is a key sign that astronomers look for when searching for intelligent life. We would be announcing our presence to the cosmos. There are also deep social challenges. How do you manage a project that takes many generations to complete? Who gets to control the thermostat for an entire civilization's energy supply? These are not engineering problems. They are questions about power and fairness. The construction of a Dyson Swarm is less a test of our technology. It is more a test of our character. It forces us to ask if we can cooperate on a massive scale. It tests our ability to think beyond our own lifetimes. It requires us to value the future more than the present. The path to becoming a Type 2 civilization isn't just about building machines. It's a choice about the kind of people we want to be. It is a promise made to descendants we will never meet. This grand project sits on the horizon of possibility. It is a monument to what a species can achieve when it works together across centuries. The question is no longer can it be done, but will we be the ones to do it? With the plan for a Type 2 civilization laid out, our view of the cosmos changes. The night sky is no longer just a collection of distant lights. It becomes a map of possibilities. Each star is a potential home for another intelligence, another swarm, another story just like our own. The search for these civilizations requires a new way of seeing. You cannot find a star hidden behind a cloud of technology by looking for its bright, visible light. Instead, you must search for its waste heat. This is the core idea behind looking for techno-signatures, the fingerprints of advanced engineering on a galactic scale. A Dyson Swarm would be the biggest machine we can imagine. Like any machine, it would not be perfectly efficient. It would leak energy. This leaked energy would pour into space as infrared radiation, a form of light invisible to our eyes but detectable by powerful telescopes. Imagine a star that seems strangely dim or blinks out entirely. But when a telescope like the James Webb looks at that same spot in infrared, it sees a huge, warm glow. This is the telltale sign. A ghost star, surrounded by the heat of a civilization capturing its power. This leads to a deep and unsettling question. It is known as the Fermi paradox. If the universe is full of stars, and some must have planets with life, and some of that life must become intelligent, where is everybody? Why is the sky so quiet? The silence itself is a clue. It might suggest that the step to a Type 2 civilization is incredibly difficult. Perhaps it is a great filter, a challenge that very few species survive. The swarm is not just an engineering project, it is a test of survival. Or maybe advanced civilizations choose to be quiet. A perfect Dyson sphere, A solid shell instead of a swarm would trap nearly all of a star's energy. It would be almost invisible, a way to exist without drawing attention in a potentially dangerous universe. There is another possibility. We could simply be one of the first. The universe is very old, but stars stable enough for life are much younger. In the grand timeline of the cosmos, we might be the first ones to wake up and look around. This search for others fundamentally changes our place in the universe. We are no longer just inhabitants of a single planet. We are active participants in a cosmic story. The decision to build our own Dyson Swarm becomes a statement, an announcement to the void. So when we look at the stars, we are also looking at a reflection of our own future. Every silent star is a question about our own potential. Will we be the ones to build that structure, to harness that power, and to become the next light in the darkness? The journey has just begun.